A coordinate system assumes a basis of some type. So let's have a basis, B1 through Bn for our vector space V. Then, for every vector in our vector space, there is a unique set of scalars which express our vector x in terms of this basis. So when I say that I'm giving you a particular vector, and we write down a set of numbers, what I'm really writing is the set of coordinates relative to a known basis. And these scalars are the coordinates relative to that basis. Sometimes we'll call them B coordinates. And if those are real numbers, then I've just turned x in terms of this basis into a list of numbers. Notice this vector is in Rn, even though x might not be. X is in any vector space V, as long as I have a basis for that vector space. So this is a way of taking an arbitrary vector space and transforming it into Rn vectors. The way we list these numbers depends on the way we listed our basis. So, an example. Let's suppose we are looking at the standard basis in R3. By the way, in physics and in Calc 3, we call these I, J, and K instead of E1, E2, E3, but they're the same freaking vectors. And I distinctly remember writing vectors like this in both of those classes. That's a three-dimensional vector, 3 forward, 4 to the left, and but really, we wrote that, didn't we? That made the assumption that our first coordinate was the x direction coordinate, I. That we would take them 3 times the vector that went this way, 4 times the vector that went that way, and -6 times the vector that went this way. And that gave me a position in 3 dimensions. But I don't have to think about just vectors in R3. So let me pick a different space. Polynomials of degree 2 or less. And I will again use the standard basis. If I'm using the standard basis, then I want you to give me a coordinate vector for this polynomial. Well, in the same way that I wrote i's and j's and k's up there in the previous example, I can say this is no 1's plus 2t's plus negative 1 t squared, right? Well, if that's the case, then the coordinate vector for f relative to this basis is 0, 2, negative 1. Now, this is a complete holy shit moment to me. I took a polynomial, f of x, f of t in this case, turned it into a three-dimensional vector. The map from a function to its coordinates maps our vector space into Rn. We're going to call this the coordinate mapping. But you've already done this. Suppose I give you a basis composed of the two columns, 3, negative 5, and negative 4, 6. And then I go so far as to tell you, hey, I've got this coordinate vector. That's the same as saying that x is 5 times 3 minus 5 plus 3 times minus 4, 6. If you calculate out that arithmetic, what do you get? This vector is in terms of the standard basis. This is 3 in the x direction minus 7 in the y direction. So this is in terms of I and j. But this was in terms of a different basis, a different place to live. I've gone the other way. I'm making this up so the numbers might suck. If I tell you up front that I have the vector -6, 8 in the standard basis, how do I get its representation in the other basis? But that was where I told you that this was the coordinates, right? That was the coordinate vector. This time I'm giving you this end. How do we get back there? I know that it's going to be some number times the first vector plus some number times the second vector, right? How do I find C1 and C2? This is an augmented matrix, isn't it? This is trying to solve for these two numbers in here. Because the first equation says 3C1 minus 4C2 equals -6. The second equation says -5C1 plus 6C2 equals 8. That's exactly simultaneous equations. How do I find C1 and C2? What do I do from here? And get what? Put it in the calculator, it's still going to look like this. What do I do to it? Reduced row echelon form. Now, as I said earlier, I just made this one up, so I haven't worked it out yet, so these numbers might just suck. So, sorry. That's why we have a calculator, so I don't have to do this by hand. Okay, so there's the matrix I want. 3, -5, -5, okay. Matrix, math, reduced row echelon form of that thing. Hey, I got lucky. So the coordinate vector is 2, 3. Now, okay, wait a second. When we talk about coordinates, I'm used to thinking of x coordinate and y coordinate. But x and y are really the I and j directions. So this is 2, 3. 2 in the what direction? No, unfortunately, it isn't in the x direction. That would be the case if we were in the standard basis, but we're not in this case. Our basis here is given by those vectors up there, right? So it's 2 in this direction and 3 in this direction. I've changed my graph paper. It's not a grid of little squares anymore. It's a grid made up of arrows pointing in this direction. Instead of x's and y's, see, little square in the x direction, little square in the y direction, I have 2 new directions. and my grid is measured relative to that at some funny angles. This works in 3 dimensions too. Crystal structures in inorganic chemistry, anybody? Look, body-centered cubic, face-centered orthorhombic, monoclinic crystals. I wish I was making this up. It's everywhere. And if I can do it in a crystal lattice, that's what I'm doing on a semiconductor surface with magnetic spots for memory chips. Anybody work on a PC? Get a blue screen of death anytime? Ever? That lovely little blue screen comes up and it says, you have an error. Big bunch of hex code, right? You know what that hex code is? It's a memory dump. It shows you where the error occurred and what was in that spot of the memory. So it went to those coordinates and read out the information there. My starting assumption is that unless I am told otherwise, when I see a string of numbers written like this, I'm assuming those are in the standard basis. So these are the 3 arrows that make up my new basis. But I've written them each in terms of X and Y and Z to start with. But maybe these point like these directions. Now I want to know where my coordinate is relative to this thing. Well, again, if I want to know what the coordinates are for this, rather than think of this way, I'm asking you how you can make this vector from these. Isn't that a column space question? I want to know if you can write this vector out of these 3 columns. That's asking, hey, is this vector part of the column space of this matrix? And the way in which you would do that is to solve the reduced echelon form exactly the way we just did up here in the 2x2 case. When we find these coordinates using the reduced echelon form, you're really finding the numbers C1, C2, and C3 that make this equation true, right? So you've worked out this vector when you did the reduced echelon form, which I'm assuming is what you are all punching buttons on your calculator doing right now. This is the coordinate vector in B. What did you get? I didn't. Uh-oh. Three rows, four columns, 1, minus 3, 2, 8, negative 1, 4, negative 2, negative 9, negative 3, 9, 4, 6. Aha! Whew. I feel so much better now. Do I hear a second on that version? Good. I'm seeing more people nodding. Did that work out that time, Shane?
Yep.
Okay, good. Okay. Wait a minute. This matrix, when I multiply this thing by this matrix, I get this one, right? This is the regular vector x. That's in terms of the standard basis, yes? Let's even write that in terms of the standard basis, s. Oh, I took a vector in b terms, and I got out a vector in s terms when I multiplied. So I am going to call this the transition matrix from B to S. Now, the textbook writes P with a subscript B. Sometimes they write it as a script P, sometimes they write it as a print P. I'm going to mess with myself regularly and screw this up. I'm not sure I like that notation. I would prefer to write this as something that multiplies and takes from B to S, right? From B to S. I've seen that notation in a lot of other places, but the textbook uses this one. I'm going to use that so that you can read the textbook to go with it, but I think that one makes a little more sense. So what that means is that if I take PB and I multiply XB, I get X in the standard, or just plain X. Questions? What can you tell me about this matrix? I promise there's a rest of that sentence coming. Did I have to do the reduced or echelon form to know that?
No.
Why not?
You could do it with the echelon form or find.
I don't even need to do either of those. Why the hell not? The columns of that matrix, where did they come from?
The basis.
They're the basis vectors, right? What was the special property about the set of vectors that make a basis? Friday.
linearly independent and span B equals H.
They're linearly independent. If I have a square matrix whose columns are independent, it must be invertible. The way we built P from a basis forces it to be invertible because we made it from a linearly independent spanning set. Oh, wait a second then. If that's invertible, I know how to find the B vector when I'm given the standard vector. How do I get X all alone up here? Sorry, XB all alone up here. I got to get rid of the P, right? Which means I move it to the other side. I multiply by the inverse. This means that the coordinate mapping that we were talking about earlier, that takes every vector and turns it into its coordinates, is a matrix transformation. And if it's a matrix transformation, it's a linear transformation. So finding coordinates takes any vector space and transforms it into Rn. But wait, there's more. This is a matrix transformation using an invertible matrix that makes this transformation one-to-one. Every calculation I would be doing in V, whatever vector space V is, can now be done in Rn instead. Instead of working over here in this space, I can work over here in Rn. Do stuff in a one-to-one fashion. That means I can then go back. So if this has some calculations I want to do, but doing those calculations suck, let's take the coordinates, do the calculations over here, and then go back. The fact that this is a one-to-one map is really a very particular example of a more general idea. This map is referred to as an isomorphism. From V to Rn. And that means iso, same, morph, shape. That means that the behavior in V and the behavior in Rn is exactly identical. And everything we do over in V has a counterpart that we do over in Rn. And I can make the calculations easier by working whichever space is easier to calculate in. But they are effectively the same thing under two different names. With that in mind, polynomials of degree 2 or smaller, we found a way to make those look like R3 vectors. So if I wanted to do my calculations over in polynomials, I could do them one way, but I could just as easily shift over to three-dimensional number vectors and do them over there, and then switch back. Now, there's a very particularly important thing here, and that's my choice of basis here matters. The way I choose the basis allows me to decide what things in V I want to emphasize or de-emphasize, and what things are important to me and what aren't. In the version we did with polynomials, I was keeping my like terms together, right? All the numbers, all the t's, and all the t-squares. But maybe I want to use a different basis. Maybe it's better for some reason to use a basis that looks like this. Well, then I might say to myself, here's a polynomial what I would like to do is find the coordinate vector in terms of that basis, right? We just set up the equations that would do this. I would say C1 times the first vector, C2 times the second vector, and C3 times the third vector. I'd gather all my like terms. No, don't want to do it that way. I'm going to cheat. And I'm going to say, let's switch from P2 to R3. And in R3, that is the coordinate vector in the standard basis, isn't it? And that is the standard basis coordinate vector for this. What's the standard basis coordinate vector for this one? Exactly. And the standard coordinate vector for this is going to be 1, 4, 7. Instead of bothering to set up the equations in P2, I'm just going to say, screw it, and set up the equations in R3. I never, ever, ever need to think about these as quadratic equations again. I just have to think of them as vectors in a new vector space. And I can move from that vector space P2 to the vector space R3 with this coordinate transformation. But notice, if I had set up, it would be C1 times 1 plus t squared plus C2 times t plus t squared plus C3 times 1 plus 2t plus t squared equals 1 plus 4t plus 7t squared. And if you gather all the t squared terms, you get C1 t squared, C2 t squared, C3 t squared equals 7t squared. Look at this bottom equation, 1, 1, 1, 7. That's exactly my t squared equation. My middle equation, no t's, 1t, 2 t's, 4 t's, 0, 1, 2, 4. I can turn any vector space on the face of the planet as long as I can find a good basis into Rn. Which means 99% of the calculations we were doing earlier for Rn apply to any vector space at all. Here's a set of polynomials. Is this set of polynomials independent or dependent in P2? I don't know how to answer that question in P2. You've never talked about independent polynomials. You've only talked about independent vectors. Oh, okay. Turn these polynomials into vectors in R3. What columns do you get when you do that? Again, I'm assuming that I'm going to use my standard basis for that. 1t, t squared. What are these as vectors? And so what I'm really asking, instead of asking if these are independent, I can ask, are these independent? How do you figure out if those three columns are independent? And do what with it? Or the determinant, or check the number of pivots, all of that stuff. How many pivots do I end up with when I do reduced echelon form? I only end up with 2. That means they're dependent. If I'd taken the determinant would be 0. Ta-da! I am 100% convinced that this question is insane as written. Can you write F in terms of P1 and P2? If you're anything like me, the answer is, how am I supposed to know? Swap them out. Move this entire question from P2 to R3. I'm using the standard basis. Now, my standard basis looks like that. So what is the coordinate vector for P1? And the coordinate vector for P2 and the coordinate vector for F. So what you're really asking is this in the column space formed by these? Which means I want to know if that has solutions or not. Which once again comes down to do the reduced row echelon form and tell me if you get a C1 and a C2. Do I have 2 pivots? I only have 2 columns. I should have at most 2 pivots. Do I have 2? Yay! And the answer is yes. Is it 2-3 or is it 3-2? 2-3. I found the coordinate vector. The coordinate vector is 2-3. 2 times P1 plus 3 times P2. in one sense, we can think of all of these equivalent vector spaces as different screens through which we view the same things, different labelings for the same behaviors. Who's taken the foreign language course already? What'd you take?
Spanish.
What'd you take? Anybody else take something different? Anybody else take something different?
French.
Un, deux, cuatro, right? Uno, dos, tres, cuatro. 1, 2, 3, 4. Uno más uno y dos. Adding, right? Doesn't matter whether I add in English or Spanish, does it? Echad, shtaim, shalosh, arba, chamesh. I don't care what language you're counting in. Arithmetic is the same no matter who does it. That's all this is. I don't want to do them in polynomials anymore. I don't like polynomials. French is oogie. Fine, think in some other language. Cuando piensas en la otra lengua, tienes que hablar con todos. I don't care what language you're speaking. You can talk to anybody. Find the hook that translates. Rn is easy. Polynomials, less so. Other vector spaces? Who knows? Can I find a good basis? Once I have that basis, can I move between bases? If I know how to get from R3, P2 to R3, how do I get from R3 to P2? It's not all that difficult, is it? This seems to be a straightforward behavior, but it's a one-to-one transformation. It's invertible. What happens when I'm working? Need that picture again. In this system, and I really want to be in this one. How do I make the shift? Or if I'm working in this system and I really want to be in this one. There's got to be a way to change from one system to another. Up here, the same way. But to do that, I need to make sure that the vector spaces match up. Match up what? More on that on Wednesday. If you came in late,